All right, guys, so this is part three of the 2015 International Free Response. We just got two more questions to go, so this should be the last part. We got question 6 and question 7. So just remember, question 6, question 7, they're the shorter types of questions. They're only worth 4 points apiece. And remember, 6 and 7, I don't know, lately, on the latest released exams, I always feel like 6 and 7 tend to be the easiest questions. Kind of like they're even shorter than some of the other questions that they're asked. They're quick hitters, boom, 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 boom. If there's an explanation needed, it's going to be 1 or 2 sentences, and it shouldn't take that long. And another thing to understand about the AP exam is chemistry can be complicated, and there are some difficult questions. There's going to be difficult questions on the free response. They tend to happen on questions 1 through 5, the more difficult questions. At least that's what I've seen. Okay, but not everything's going to be super difficult. Okay, not everything. Some of it is going to be really easy. Just what's an electron configuration or something like that for just a neutral atom or something. So a lot of the things, a good amount of the topics or the questions are going to be really not that difficult. And one of the errors that I think a lot of students make is making the question more complicated than what it is. And so figuring out what the question, cutting through all the fat, this big long paragraph of what's going on, all of these reactions, like in question number 3, they gave you all those equations, all those reactions. It's like, yeah, we kind of needed to know it a little bit, but it wasn't that difficult. So cutting through all the fat, all the stuff they're trying to throw at you to distract you, and getting to the point. Okay, so let's pick up where we left off on question 6. Okay, so question 6, boom, we get a PES, and again, I always note this, but I've never seen it the other way around. But notice it's higher binding energy to lower binding energy. So this is going to be the sublevel closest to the nucleus, and this will be the sublevel further away from the nucleus. And if this is a full spectrum, we can identify the element right away. 1s2, 2s2, and then let's count. 2p, this would be 2, 3, 4, 5, so 2p5. So I know the element's fluorine right off the bat just by the PES that's given to me. Okay, they give us the energies for each peak. So they tell us the energies for each peak. Remember, binding energy is kind of synonymous with ionization energy, but this would be energy per mole of electrons. So if you wanted to, let's understand, if we wanted to know the first ionization energy for this element to remove just a single electron, we would have to divide this by Avogadro's number to get the energy for a single electron, because this is energy per mole of electrons, right there. Okay. Here they give us the frequency. I just made a little note to remind you what that symbol is. It's on your formula sheet. It reminds you. Okay. But it says the complete photoelectric spectrum, which we just identified the element as fluorine, so it's not an unknown element to us anymore. The frequency ranges are the different regions of the electromagnetic spectrum, which is just different frequencies of light, given in the table. Okay. To generate the spectrum above, a source capable of producing all the light with an energy of 7 times 10 to the negative or to the fourth. Okay, so 7 times 10 to the 4 kilojoules per mole of photons was used. Such radiation is from which region of the electromagnetic spectrum? So they give us energy, and we just have to solve for frequency here. So E equals h nu, and again, this equation's on your formula sheet. It tells you that this symbol means frequency, and that's what this is right here. So we have energy, and H is Planck's constant, and it's on your formula sheet, 6.626 times 10 to the negative 34 joule seconds. Okay, so all we have to do is divide the energy by Planck's constant, but we got to be careful. This is energy in kilojoules, but we need our energy in joules to do this. Okay, So if we go to the scoring guide, let's see how they did it. All right. So we need to figure out the energy for a single photon, not a mole of photons. So we have to take our energy, divide it by Avogadro's number to get energy per photon, and then we have to multiply by 1,000 to get joules. Then once we have the joules of a single photon, we would plug it into E equals h nu and figure out the frequency. And so they give us the frequency 2 times 10 to the 17th, so it would fall within this range here. So X-rays. Okay, so again, that's using E equals h nu. Now the complicated one is, a lot of kids are just going to plug in this number in for E, and then a lot of kids are just going to multiply by 1,000 and convert that, but that's per mole of photons, and E in the E equals h nu is the energy of a single photon. Okay. Student examines the spectrum and proposes that the second ionization energy of the element 3.88 times 10 to the third kilojoules per mole, or is the second ionization energy. To refute the proposed interpretation of the spectrum, identify the following. Okay, so remember, second ionization is the energy required to remove the second electron, not the second furthest energy level, right? So this is the second furthest energy level or sublevel from the nucleus, 2s, but there's 5 electrons here. So you'd have to remove 5 electrons from fluorine to start thinking about removing one of these electrons. Okay, so the second ionization isn't going to be this energy here. It's still going to be around that energy here, okay? So the subshell from which the electron is removed in the second ionization energy should be from the 2p, right? First ionization would be from 2p. Second ionization would be from 2p. Third ionization would be from 2p. Fourth ionization, 2p. Fifth ionization would still be from the 2p sublevel. You wouldn't get to the 2s sublevel until you got to the 6th ionization of fluorine, okay? The sublevel that corresponds with the second peak is 2s. So that's our answer. The furthest peak there is 2p. That would be where the second ionization, the first, second, third, fourth, fifth ionizations occur, and 2s would be the second peak there. All right, so 2p and 2s, boom. And look, that's all you needed to write. It didn't say to justify. Okay, so your answer for B1, all you had to write was 2p. Your answer for B2, all you had to write was 2s. That's it. Okay, move on, right? We're moving on to question 7. All right, so part A may be a little bit difficult because if you forgot to figure out just how much energy for one single photon instead of a mole of photons and maybe forgetting to convert to joules. But, 2p and 2s right here, boom, boom, 2 points, and I'm moving on. Okay. All right, so here we have an acid acting like an acid in water. All right, so the molecular formula of this acid, also known as aspirin, okay. We're given the ionization of it or the dissociation of it in water. We're told a pH of a 0.01 molar solution is this. So remember, if we just do 10 to the negative this, that would give us our hydronium concentration, which would equal this ion concentration too, all right? It says write the Ka expression, so that would just be, Ka equals products over reactants, don't include the liquid water, all right? Calculate the Ka. So we can use kind of our shortcut. We can say Ka equals x squared over the concentration of the acid, but we're not going to be able to use the 5% rule. So what we're going to have to do is Ka equals x squared over this concentration minus x. And what does x represent in that shortcut? It represents this concentration. And this concentration can be calculated by doing 10 to the negative 2.78. So what we're going to do is 10 raised to the negative 2.78. That'll give us this concentration, which is also this concentration. So all we have to do is that squared to give us our numerator. And then what we have to do is 0.01, okay, 0.01 minus this concentration, which is X, to get our denominator. And then we'll plug that into the Ka expression and we'll solve. Okay, so did I do it? Yeah, so this I did it here. So, right, it's kind of the shortcut, but you can't do the 5% rule. Because if you notice, X ends up being 16% of 0.01, so the 5% rule doesn't apply here. Okay, we only invoke the 5% rule if we have to graph to solve for X. We don't have to graph to solve for X. We get X in this shortcut by knowing that we're doing 10 to the negative pH. So that gives us our X value in our Ka shortcut without the 5% rule being utilized. We'll square that to be our denominator or numerator, and then 0.01 minus that will give us our Ka. All right, and so that's our Ka. Let's just double check. Yeah, we got the same answer. Good. And the last question of the test: an aqueous solution of aspirin is buffered to have equal concentrations of this and that. So you got a buffer solution, and they're equal amounts. Henderson-Hasselbalch, or just remember, when you have equal amounts of your buffer components, pH equals pKa. So all you have to do is take the negative log of your answer from part B, and you got it. And it would read down. So even if you didn't get this right answer, or you didn't know how to do it, make something up. Hopefully you understand Ka's have to be less than 1, because it's weak acid. The equilibrium is not favored to the right, it's favored to the left. So if you do make up a Ka value here, make sure it's less than 1, okay? And then for this answer, all you have to do is take the negative log of it, because you have equal amounts of your buffer components. And so that's all we would have to do. So they're showing the Henderson-Hasselbalch, but remember, because these are equal, that's 0, so pH equals pKa. So the negative log of our answer from part B gives us our answer to part C, and we're done. We finished the test, and we got 46 out of 46 points. And that means we got 100% of the free response. So hopefully we did just as well, or maybe not as well, but pretty good on the multiple choice, and we get a 5 for the exam, and we're happy. And then we're chilling. All right. So hopefully, this is yet another video of me going over yet another free response. So hopefully by now you've watched them all, and you're feeling very confident about your free response on May 1st. All right. Have a good one.